The law of large numbers says that if you toss a coin many times, then you should expect to get whatever you're going to get. But, once you toss it a lot of times, eventually the probability of what you will get closer and closer and closer to that 50%. It's not going to start out at 50%. You're probably going to start out at 30% or 40%. But once you toss it like 100 times or 1,000 times or 10,000 times, you're going to get really close to that 50%. And that's what the law of large numbers says. The longer you do the experiment, the closer you're going to get to what the theoretical probability is. So that's the law of large numbers. Other than the law of large numbers, we have something called expected value. With expected value, when you go out and you purchase a ticket in a game of any kind, then you expect for you to possibly win that game. But regardless, that ticket has a price. It's not the price that you paid for it, because you could win. But even if you win, there was some value to that ticket. And that value is technically the same whether you won or whether you lost. So if you were to win every single prize and you were to lose every single prize, that value should be the same. It's the expected value. So if you were to go out and win every single ticket in a raffle, go out and buy every single ticket in the raffle so that you could win the one prize that they had, then the value of each ticket that you purchased would average out to be the same. Even though you won that one thing in the raffle, each ticket would average out to be the same value. And that expected value is what we're talking about. So if you were to go out and purchase every single lottery ticket that there was for that $1 billion prize that they have, then each ticket would have an expected value. So we're going to talk about how to figure out what that expected value is. Expected value is equal to the value of event A times the probability of event A actually happening, plus the value of event B times the probability of event B happening, plus the value of event C times the probability of event C happening, plus so forth and so on, all the way through all the different events that could happen. It's not as complicated as it sounds in the directions here. Let's say your school is raffling off a season's pass to the local theme park, and that value is $200. If the school sells, so they're selling off a season's pass to a theme park for $200. If the school sells 1,000 tickets, for $10, then the average loss per person is $9.80. So each person is buying $10 ticket. So they're losing $10. Each one of them is losing $10. But they have a chance to win $200. Well, a $200 theme park pass. And I know that it's out of 1,000 different tickets because they told me they sold 1,000 tickets. So when I figure this out, they lost $10. But here, the 200 times 1 divided by 1,000 is equal to 0.2, which leaves me at them losing $9.80. So the average loss per person is $9.80. That's how they got that. That's what the expected value is. So everybody who bought a ticket lost $9.80. One person gained. We don't know who, but one person did gain. But for the most part, everybody lost $9.80. And even the one person who gained lost the $9.80. Because it's an average. So, right here, you roll a single fair die, and here's what happens for each result. You have all of these different possibilities. They want to know, is it a good game for you, and what is the expected value for one game? So, we'll figure out the expected value. Probability, I don't want to write it like that. Hold on. I want to say it like that. I don't want to write it like that. So, right here, we have 6 different things. The probability of getting 1 is 1 out of 6. And we could win $3. So we'd be up by 3. Plus, the probability of getting a 2 is 1 out of 6. And we would have 0. Plus, the probability of getting a 3 is 1 out of 6. And we would win nothing. We would lose $5. Plus, the probability of 4 is 1 out of 6. And we would win $3. Plus, the probability of a 5 is 1 out of 6. And we would lose $4. Plus, the probability of 6 is 1 out of 6. And we would win $2. Here, 1 times 3 is 3 over 6. That is 0 over 6, or just 0. That is negative 5 over 6. 3 over 6. Negative 4 over 6. And 2 over 6. When I add these up, that's negative 2 over 6. Negative 1 over 6, that's negative 3 over 6, that equals negative 1 over 6. So we lose $0.17 per game. What is the expected value if 500 games are played? 500 times 0.17 is equal to $85. A loss. A loss of $85. A loss. A loss. A loss of $85. Gotta keep up with that. So not all games are good. You usually expect not all games to be good, but everybody plays the games because you never know. You might win. Obviously, you're going to win more than you lose. It's more of a chance of winning than losing. Not all games are set up for you to lose. For example, there's this game. You're given 7 to 2 odds against rolling 2 even numbers with the roll of 2 fair dice, meaning you win $7 if you succeed and you lose $2 if you fail. Use the table to find the required probabilities. So, first of all, they want us to roll 2 even numbers. So for that to happen, we can't have odd numbers in there. So I'm going to take out all the odd numbers. So the only place where we're going to be rolling 2 even numbers are going to be here. That's only 9 times out of a total of 36 numbers, which is a quarter of the time, just so we understand one another. So they say we win $7 if we succeed. So we make $7. So the probability is 1/4 and we win $7. That's good. Or 3/4, because that's the other part. Right? That's the other section of it. 3/4 and we lose $2. Well, 1 times 7 is 7/4. Plus 3 times -2 is -6/4. That still leaves us in the positive 1/4, 0.25 for our expected value. It's 25 cents for our expected value. 1/4. What can we expect if we play 250 games? 250 times 0.25 is equal to $62.50. Does that mean we're actually going to win $62.50? No. What we actually do and what the expected value is, two totally different things. But kind of positive. The expected value is kind of what is leaned towards, just like the law of large numbers leans towards theoretical probability. It's the same kind of thing. Because the law of large numbers leans towards theoretical probability, expected value is what is leaned towards in games. So eventually, in games, it's going to be leaned towards. That's why the house always wins. You keep playing, the house is going to win. That's because the games are keyed that way. Doesn't always happen. Usually happens because of expected value. Averaged over 250 games, you should expect to win $62.50. An insurance policy. In the past, this was the one that was on the final. We just, in the past 2 days, rewrote the final. So this is no longer the one on the final. I know, I was the one who rewrote it. I'm sorry this one's not there anymore. I liked this question. They rewrote it to a different expected value question. It's really close to this one, but it's not insurance anymore. So I don't get to say it's just like this one, but it's kind of close to it. An insurance policy sells for $325. Based on past data, an average of 1 in 100 policyholders file a $10,000 claim. An average of 1 in 250 policyholders will file a $25,000 claim. An average of 1 in 500 policyholders will file a $50,000 claim. Find the expected value to the company per policy sold. I think this one was taken away because this isn't really how insurance works. So the insurance policy sells for $325. So the company gets the $325 all the time. They will always get that. That's what the 1 is for. They will lose $10,000. 1 out of 100 times. They are going to lose $25,000. 1 out of 250 times. They are going to lose $50,000. 1 out of 500 times. So this is going to give you the 325 plus the 100 plus the negative 100 plus the negative 100, which gives you a positive 25. So they're making $25 off of each one. So the expected value for each is $25. So when they sell 100 policies, 100,000 policies times the 25, that's $2,500,000 that they profit. And we'll get to the other one in a minute.